Hello and welcome to the third video on 3D printing for repair. In this video, we will take you through the redesign phase. After this video, you will understand the differences between injection molding and 3D printing. You will also learn how to design your part for 3D printing. In the previous phase, you analyzed your part and decided that you could print it. Now, it is time for the redesign phase. This is the second phase of the 3D printing for repair process. In this phase, you will find out how you can apply the findings of the analysis phase in the redesign of your part. In the redesign phase, we will focus on two main topics: injection molding versus 3D printing with FDM and redesigning for FDM. The goal is to give you the tools for you to design and model a 3D printable version of your part. Keep in mind that there are several 3D printing methods out there, but in this video we will focus on FDM since it is the most available and most common method out there. FDM stands for Fused Deposition Modeling. This process is also known as FFF, which stands for Fused Filament Fabrication. The most important thing to know before we start is this: you cannot make an exact copy of the original part and 3D print it. The original part was made with a different manufacturing method, so a direct 3D printed version will not have the same properties and strength. Therefore, you will have to think how to optimize your part for 3D printing. So let's compare 3D printing with FDM to the original manufacturing method. As most parts that are considered for 3D printing are injection molded plastic parts, we will use this method for the comparison. So, what are exactly the differences between injection molding and 3D printing? We will study these differences by looking at the process, the parts that can be produced, and also the performance of these parts. These animations show how the machines for injection molding and 3D printing work. Injection molding is done by pushing molten plastic into a mold. The shape sets by cooling the plastic and then pushing it out of the mold. 3D printing is done by melting a plastic string, also called filament. The shape is built up by printing a filament layer upon layer via a moving printer head. Each manufacturing method has pros and cons. Injection molding can be very precise and create parts with high tolerances and detail. However, part geometry is limited as you need to be able to get the part out of the mold. 3D printing, on the other hand, works without a mold and therefore is able to make very complex shapes. However, 3D printing is less accurate due to the movement of the printer head, and this means that 3D printed parts have limited tolerances and detail. The different manufacturing methods provide differences in the internal structure of the part as well. An injection molded part is a solid object. A 3D printed part is layered and not completely solid. It has a near solid shell and an infill pattern and density. Even with 100% infill, there will still be cavities and gaps inside your part. The difference in structure is the main reason why injection molded parts and 3D printed parts perform differently. Even if parts are made from the same material, 3D printed parts are less strong, less flexible, and less impact resistant. With high forces across layers, the layers can be pulled apart from each other. This makes parts especially weaker along the set axis, as you can see in this picture on the arms of this part. But how do we design for FDM printing? And how do we overcome the challenges of the new manufacturing method? To answer these questions, we will look at the following topics: printing direction, the design guidelines, how to rethink your part, and how to ideate and simplify. Let's start with the printing direction. This is one of the most important considerations for 3D printing with FDM. As we mentioned before, parts are weaker across the layers. Therefore, it is important to keep the printing orientation in mind when designing. Make sure that the sections that need to withstand forces are oriented in the strongest position as shown in this diagram. In some cases, there are multiple sections that require strength, but they are pointed in different directions. For example, this often happens in parts that have a lot of snap fits. In that case, you can split the part to optimize the strength in these directions. There are design guidelines out there that will help you design your part and make it ready for FDM 3D printing. For example, this image shows a list of guidelines designed by 3D Hubs. You can use these to find things like the minimum thickness of your walls or the maximum angle of an overhang. It is important to consider these guidelines when redesigning your part. You can find these and other guidelines online or through our 3D Printing for Repair guide and videos. So let's jump into rethinking. The first step of rethinking your design is to choose your material. During the analysis phase, you identify the performance requirements of your part and maybe even the original material. You will now have to choose a material that suits your part needs. There are many different 3D printing materials to choose from. Examples of common materials are PLA, ABS, PETG, TPU, and nylon. All these materials have their own specific properties. They vary in quality, price, and performance, providing different strength, flexibility, and temperature resistance characteristics. In the 3D Printing for Repair guide, you will find help in choosing the right material for your part. We also recommend looking into the technical datasheet provided by the manufacturer to find further information on the performance of the material you choose to use. Let's also take a look at how we can rethink part design. In the analysis video, we already showed that you can simplify details and shapes if they are not essential. Besides this, you can also increase the sections of the part to make them stronger. These are the several iterations of the kettle switch redesign. We increased the thickness of the arms to make sure they wouldn't break again, and we also simplified the double curvature at the back to make it easier to model and print. Earlier, we explained that you can split the part to optimize the printing direction and make the part stronger. You can also change the shape of a part to overcome material differences. For example, the geometry of this part in the picture compensates for the lack of flexibility of the 3D printing material, compared to the rubber of the original part. This example also shows a component that is designed to be printed in two sections to avoid weak points from sections oriented in different directions. Playing with your printing direction, simplifying, and redesigning your part can also make your part easier to print and reduce printing time and material use. For example, the image shows the effects of the printing direction and redesign for a part with a rounded top. The original part on the left is printed upright and has a long printing time, a rough surface, and high material use. The redesigned part on the right has a flat top and is printed upside down, giving a smooth surface and reducing printing time and material use. So there you have it. In summary, it is important to consider the differences between the original and the new manufacturing method, and how this affects your part. For example, 3D printing can have lower performance but higher form freedom compared to injection molding. To make up for the difference and improve part performance, you will have to rethink your part specifically for 3D printing. Finally, rethinking your part design and simplifying it can also save printing time and materials. In our following videos, we will dive into the topics of digitizing, modeling, and manufacturing. See you then!